Okay. So sorry about the confusion there. I don't know what exactly has happened with YouTube, but I don't have any video feedback as far as YouTube is concerned, so I'm not 100% sure exactly what you all are seeing. I only see the video feedback from the like undelayed feedback, which is normally what I pay attention to anyway. But if if the video starts bugging out for you all, you'll have to let me know that nothing's going on. I don't quite understand what's going on. Like I said, I used this for months and never had this particular problem, so I don't know what's going on. It seems to be on YouTube's end though, because it wasn't just this aspect that was going wrong. It was my whole YouTube account was I was having issues. Even like deleting old test streams, making sure that this worked last night. But anyway, so in case you didn't see it, I posted the tentative syllabus slash lecture schedule earlier. So it's under syllabus on Elms. So I'll quickly read over that. Although you should read over it yourself. So I'll be adding to the lecture schedule. I'm probably going to add like a week at a time, basically. So I've got if you look at the bottom of the syllabus on Elms, I have like the first like week written out for what we're going to be covering. So anyway, welcome to number theory. So this is a fun course because um, there's quite a bit of time we're going to have at the end. Maybe like the last even like 3-ish days are kind of going to be free for us to kind of go in whatever direction we want to. So I'll uh, I'll ask your opinion on what it is you want to what direction you want to go when we get there. So like the last 3 days will be fun stuff. That's what I'll call it. But anyway, so the course is going to cover what happened here. Video is oh wait what is going on? Something is weird. My This is really weird. My view all changed and now it acts like I am no longer live. Hmm. Very, very weird. In fact, it acts like the stream is cut off, so someone type in chat if they still see stuff happening or still hear me. Otherwise, this is not looking good. I'm still live. Okay. This is extremely weird. Huh. Well, in like roughly, I guess 10 seconds. Yeah, this is really really weird. I don't understand what's going on. You sure it's not a still? I'm still live. At least you're still hearing my voice. Wait, I'm gonna write something. So here, here. Right. This is like a like a tiger or something. Right. Like there. This is tiger. Is there motion? You saw the hand. Okay. All right. So moving. All right. Well, that's good. Okay. Okay, amazing. Like I said, this is really weird. I'm not really sure what's going on here, but okay, whatever. So yeah, so there's a slight delay. That's not the issue. The issue is that my view currently right now is of a paused video, and it's acting like I've essentially already uploaded like the stream, and we are not live. Like in fact, next to the little live bubble, um, it's like gray instead of red. But anyway, uh, it's what is going on here? This is This is extremely weird. Anyway, okay, whatever. So I'm just gonna keep going. This is gonna be a little bit weird, as I said, because of this bad view I've got going on, but it's all right. So anyway, getting back to what I was saying. First of all, maybe I should mention textbook. Here's what the textbook looks like. So I'm going to be following the textbook pretty closely. Textbook is, in fact, all of the references in the lecture schedule that I make, all of those parenthetical numbers are referring to sections in the textbook. So one is just like an introductory chapter, so we pretty much start immediately with chapter 2. And you'll see that we pretty much follow chronologically. There's a few sections that get tossed out along the way, but we're gonna follow the textbook pretty closely. Essentially from chapters 2 till about chapter 15, and then we're gonna kind of do our own thing after that. Obviously, this is a summer course, so things are gonna be more dense and expedited. So you obviously have gone into this knowing that. So what that means is that our first midterm is going to be not this coming Friday, but the Friday after. The second midterm will be 2 weeks after that, and then the final exam will be a further 2 weeks. So we have a nice blocking up of the course where first 2 weeks of the course are covered by the first midterm. The next 2 weeks are covered by the second midterm, although of course naturally the way that this course goes is that there's obviously knowledge that you're going to need from the first 2 weeks for that material as well. So it's not neatly blocked up. It's more like a building thing. And then the final will be cumulative, but I'm going to focus mostly on the stuff that we do in that last little bit. Although like I said, there's going to be some fun optional stuff, and some of that stuff is not going to be on the final exam, but I'm getting ahead of myself, so I'll talk about that stuff later. Anyway, so lecture format is when things are going correctly. Lecture format, I will, for the first week, just to make sure that all this is working, I will post a link and an announcement, maybe like 10 minutes before lecture starts, and then at 11 I'll start. So it's going to be every day. It's going to be synchronous. One exception that I know of already, Wednesday morning. So Wednesday's lecture is not going to be synchronous. I'll upload it some other time on Wednesday. But other than that, all the other lectures should be synchronous. So yeah, Wednesday's lecture I will upload at some other point in time. But other than that, like I said, everything should be synchronous. So we'll meet the same time every single day. It will be YouTube live stream as you're seeing. So you have any questions, you can post them in the chat. 6.4 seconds. That is pretty quick, because normally I think it was more like 15-ish seconds, something like that. So anyway, yeah, and you can, obviously the point of doing this live and live stream like this is any questions you have along the way. I'll periodically refer to chat and answer them as I'm going along. In general, after lecture's done, I'll stick around for like a few minutes to tidy up the questions in chat. So this is how lecture's going to go. As I point out in the syllabus, there is no time-sensitive synchronous assignments during class hours, meaning I'm not going to have you guys doing an assignment that would require you to be here during the even though the lectures are going to be synchronous and all that. I'm not going to give you any assignments that require you to like be here during lecture to do something. And also in the same vein, I'm not going to assign homework during a lecture and then not say anything. I'm not going to be lecturing and say, here's a list of homework problems, turn them in tomorrow, or, I want you to submit them tomorrow. Oh, I just noticed that for the homework, I didn't actually say the format that it would be in. I just said homework will be assigned, but obviously you guys are going to be turning it in via Elms, so you're going to be uploading it as a PDF to Elms. So the way that this, getting back to what I was saying. So during lecture, I'm not gonna just assign a list of problems and then like they're only gonna show up in lecture. Anytime I assign anything that's going to be graded, I will have an actual announcement that accompanies it. And that's why after the first week of classes, I'm not going to announce the lecture. You just show up at the time on the YouTube channel. I'm going to make the live stream public to try to avoid. I think it would have been fine earlier if I left it unlisted and just linked giving you guys the link in Elms. That's what I tried to do originally, but I was worried at first that having it not be public was the issue, and I don't think that's the issue. But anyway, it's going to be a public live stream, so you can just join it from the channel. But like I said, for the first week, I'll keep posting links, but so that I don't completely clog up the announcement feed, I'm going to stop doing that after the first week. So any homework assignment that I assign is going to have an announcement, so you don't have to worry about missing, what I say in like a few minutes of lecture and missing out on a homework assignment. So again, because the course moves fast, typical homework schedule doesn't quite work. So if I assign homework, it'll typically be due within like 1 or 2 days, sometimes even the next day. But because of that, I'm not going to make the homework assignments long. So even if I assign homework on a Wednesday and it's due on Thursday, then it'll typically just be a few problems. You can work in groups on the homework. Like I said, the format of the homework is I will post exercises either from the textbook or exercises that I just write and post. And then you do the work and you use your phone to upload it as PDF, and you can just upload it on Elms. So on Elms, I will make all of the proper columns in the grade book for all those homework assignments. You just upload your homework assignments by the due date, and that's it. So with the exams are going to be similar. So I already mentioned those dates for the exams. You'll be given the exam the day before, and then it'll be due by like midnight on the day of that I mentioned. So your first exam's in 2 weeks, then 2 weeks after is your second exam, and 2 weeks after that your final. And when I say that you have your exams, I mean that they're going to be due those days. What else? Yeah, you can see the grade. You can look at the grade breakdown in the syllabus yourself. Office hours. So right now my plan is to hold office hours every Friday from like 2 to 3:30. So they will also be a YouTube live stream where I just sit and wait for you to ask me questions. Either about old homework or just any textbook problem you were working on and wanted help with, any kind of thing like that. Also, there's plans to have a 406 specific tutor provide help via Zoom sessions that you're going to be able to access directly from the Elms page, but that hasn't been set up yet. So as soon as that's set up, I'll let you all know. Open or closed book exams. Open book exams. So I'll mention more about that when I actually post the exams. Basically, you're not allowed to collaborate with other students, but there's not that many rules other than that. So like I said, I'll mention more of that later. Okay. This is really weird, but it seems like I'm still live, so that's good. Okay. What else? Think that's more or less everything that I wanted to cover. As I said, yeah, I'm going to be following the textbook really closely, so textbook's important, and it's a good book too. So. So I think that's more or less everything I wanted to say. So anyone have any other preliminary questions before I get going? I can't remember if I'm missing out on something. Okay. So, um, where to start? So, there's actually some interesting. I'm not gonna go through it piece by piece, but there's actually a really, really nice intro chapter, I should say. So the chapter one's only a few pages long. It's like 8 pages long, I think. In the textbook gives kind of a nice overview of some historical results in number theory. So it highlights that there's what's the name of it? There's a Babylonian clay tablet. It's Plimpton 322. It's about 4,000 years old, and basically it's a recording. Using wedge writing, it's a recording of Pythagorean triples. Right. So, which is interesting because it's an instance of people almost 4,000 years ago that were interested in integer solutions to equations like this, right? So you have equation like this, and you want to know integer solutions to this thing. Well, you already know that these are the Pythagorean triples. So it's interesting to think that, almost 4,000 years ago, there were people writing down integer solutions to this very equation, on clay tablets for no real practical purpose. So you might immediately think, oh, well, they were doing this clearly because they needed to solve some geometry problem, right? Building something, they needed to, find the links involved of sides of right triangles. But it's not the case because they recorded values of these things, solutions of these things that were way, way too big to be practical, in any kind of building thing. So this is an early example of numbers being studied, solutions to this thing, numbers being studied just for the fact that it's interesting. In fact, one of them, so they even list this in the textbook. So the textbook lists one particular example of this. So of course we know, 3 squared plus 4 squared is equal to 5 squared, right? That's everyone's favorite Pythagorean triple from high school. But apparently one of these also included in this same clay tablet is 12,709 squared plus 13,500 squared is actually 18,541 squared. So both of these entries show up on this clay tablet. So this clay tablet is Plimpton 322, I think is what it's called. So yeah, both of these entries show up, which is pretty interesting. Of course, I think it's in base 60 instead of base 10 because Babylonian number system was in base 60. Okay, so anyway, this is one, ancient historical example of numbers being studied for properties that weren't related specifically to just like absolutely mundane, counting or measuring or something like that. So you all know or probably you've heard, if you've had a course with me before, you've probably heard me recount this before, the story of the discovery that square root of 2 was irrational, right? So the idea was that the Pythagoreans thought that the entire universe could be expressed in terms of just integers and ratios of integers. So integers and rational numbers. And of course, the first thing that comes to your mind is square root of 2. And in terms of learning math proofs, right, probably one of the first math proofs you ever saw was the proof that square root of 2 is irrational. So this was still a thing to be discovered for people that thought that everything could be expressed in terms of rational numbers. So probably know the story about how the person that discovered it was immediately thrown overboard, supposedly for ruining their outlook on the universe. Anyway, so numbers have been studied in the past, even in the far past, purely for their for the interesting properties they possess, not necessarily because of any practical application. So anyway, first chapter, you should peruse it. It's pretty interesting. So it gives some examples like naturally what arises out of a study of equations like this, or a study of generalized things. So what about integer solutions to this equation? Or we just keep going, right? So what about this generalized equation? So this is just a straight generalization of the equation that gives us Pythagorean triples. What about integer solutions to equations that look like this? So you might have already heard that this was exactly the subject of Fermat's last theorem, which is a really famous result in number theory that was eventually proven in the 90s. So that might sound like a long time ago, but in terms of math, something being proven in the 1990s is like brand spanking new. That is like as new as it gets, because to put it in proper perspective, right? If you're doing any math that you're doing in a math course, 300 or below is like 250-ish years old at least. So you're not even doing math that's like only 100 years old until you're doing like the absolute like end of your undergrad career, and that's if you're a really, really motivated student. It's hard to get to that point. It's not until you're in grad school that you're doing math that was and done in the last like 50 years for the most part. It's a little bit different for applied. If you go into applied math, it's a little bit different. But in pure math, that's very much the case. If you're talking about math that was done in the 1950s, that's like brand new stuff. So anyway, so Fermat's last theorem was just a simple statement about the lack of solutions to this equation when n is greater than or equal to 3. So I'll go back to that as a good example, because one of the coolest things about number theory overall is that, maybe I'll write this down. So if someone had to ask you what it is that's coolest about number theory in general, one of the coolest things about it is you got hard problems that are still open. So completely open problems that are still unsolved, some of which that are easy to state. So easy to state, not always, sometimes. So an example of this is the notion of twin primes. So we're going to talk about very quickly, very, very shortly, we're going to talk about prime numbers and divisibility. So question is, when you're talking about prime numbers or when you're talking about divisibility, it's natural that prime numbers come up almost immediately. So all of you know what prime numbers are. But what is a twin prime? A twin prime is two prime numbers, so it's a pair of prime numbers that only have one number between them, right? So you can immediately think of say 29 and 31. Those are two twin primes. Can probably think of some more here. There's obviously some more trivial examples that you can list out, but here's 29 and 31. That's one example. So they're pairs of primes that only have a single number between them. You already have probably seen in some proof course, or you've seen it proven in some place, that there's infinitely many primes. You might reason that knowing that there's infinitely many primes, understanding what twin primes are, you might assume that it's not a big deal to show that there's infinitely many twin primes. But you'd be wrong, because it turns out that it's unknown currently whether there's infinitely many twin primes. So prime numbers like this, it is currently unknown whether or not there's infinitely many of those. That's a really big open problem in number theory. So That is that's an open problem that I could easily state. You could explain this to, elementary school aged children because they understand what prime numbers are. So it there are problems that are extremely hard. Even Fermat's last theorem could be explained to a high school student. No issues. Fermat's last theorem is a statement that this equation has no integer solutions when n is greater than or equal to 3. So, but it turns out that proving that is insanely hard. It goes through a lot of really, really advanced areas of math, some real cutting edge stuff. So anyway, this is in contrast to most other fields are not like this. Usually the harder the problem is, the more convoluted the statement is, because the thing that you're proving something about is already such a complicated object that just to understand all of the terminology that's being used requires, like years of coursework in that subject. So, if I wanted to try to explain to you, a like state-of-the-art open problem in real analysis or even most differential geometry stuff, it would be hard for me to find problems that would be easily explainable, especially one that would be easily explainable to like an elementary age kid. Anyway, so that's one neat thing about number theory, and you'll get a sense for that as we go through the course, because you will see that recurring a lot. So anyway, the rest of chapter 1 is just goes over how there's a lot of overlap. Those of you that have had a course in algebra will see the relationship that some of this stuff naturally has with algebraic structures, although we're not going to really go in that direction, and none of that is required to do what we're going to do. But of course, when you do number theory at a higher level, all that machinery is brought to bear on it. So that's kind of the approach that seems most natural. But number theory overlaps not just algebra; it overlaps analysis. In fact, one of the big statements in number theory, one of the it might be one of yeah, I mean, I would say it's definitely one of the biggest number theory results, in the last 150 years, is called the prime number theorem, which says something, we'll talk about it later, but it says something about the distribution of primes, basically, or roughly how frequently primes occur. And it turns out that the prime number theorem is just really, really, really hard to prove, but it is really an analysis thing. So the prime number theorem uses a lot of complex analysis arguments in its proof. So really the proof is almost entirely in the realm of analysis, and it might not on the surface look like it has much to do with number theory, but it definitely does. And so that's a common thing. So Fermat's last theorem, of course, intersects a lot of different, the proof of it intersects a lot of different fields. So it can be pretty unintuitive, where things come from. Anyway, let's go ahead and start with the absolute basics, though. So divisibility. So why do I want to talk about divisibility in the first place? The idea is that if you think about operations you can do on two integers, right? So if I take two integers, so if I let a and b be integers, so I can add them and I get an integer, right? The sum of two integers is definitely an integer. I can multiply them, and that's definitely also an integer. If I want to think about the inverse operations as honest-to-God operations, of course, I can subtract an integer from another integer, and I get an integer. But it's this last operation that... Is that the case? Well, I mean, sometimes, right? So, like 6 over 3, That's 2, and that's an integer. But 5 over 2 is not an integer. Okay, so yeah, sometimes a over b is an integer, but many times it's not. So in that case, I wind up with this operation, division, that's just not closed, right, in general. So I very much want to know when this thing is an integer, right? So you may have referred to this in the past as, oh, we say here that 3 evenly divides 6, whereas 2 does not evenly divide 5, but we're just going to get rid of that word evenly and just use the word divide. Okay, so quick definition. So given 2 integers, a and d, I'm just going to use the same notation for the statements, the definitions as the textbook, although in the proofs I'll typically use whatever notation I feel like. So given 2 integers a and d with d non-zero, we say that d divides a. In definitions, I'll typically underline the term that's being defined. So we say that d divides a, which we write as d vertical bar a. So you read this as d divides a. So we say d divides a if there is an integer c with a being equal to c times d. Okay. All right. So, what are some examples, right? So, obviously, 3 divides 15. Why does 3 divide 15? Well, 3 divides 15 because 15 is equal to 5 times 3. Right? If an integer does not divide another integer, then we use a different indicator. So for instance, 2 does not divide 5. Right? So if no such integer exists, we say d does not divide a. And we write d does not divide a. Okay. All right. So, you might already be thinking about what I'm going to say next, and the question is, does 0 divide 0, or can 0 divide anything? So, question. What to do about 0 dividing a, or 0 dividing 0? So, the thing is that could we define 0 to divide 0 in this definition? We could do that if we really wanted to, but there's no real benefit to this, and so it's actually best to just ignore all this entirely. So we never consider 0 a divisor. Okay, you can think of that as purely like a bookkeeping thing just because we don't want to deal with it, and we're not really this is not a really interesting thing to talk about anyway. The other thing to mention, so another question. Well, if d divides a, then D divides, minus, then D divides minus A, I should say. What did I say? I think I said the opposite of what I was going to say. Minus D divides A, yes, not D divides minus A, although, like I said, I could say that just as well. So if D divides A, then minus D also divides A. I guess my question here, since I put a Q here, I should say, is this okay? I mean, it's a true statement, so I don't really have much of a choice here as to whether or not this is okay. But so what am I saying? Well, using our definition of divisor, we just cared that it was an integer. So the point is, when I'm saying is this okay, typically when I talk about the set of divisors of a number, I only care about the positive divisors, because this fact, I'm not getting any more info out of this, right? Slapping a minus sign in front of it. Well, so the answer is yes, but when we speak of divisors of a number, we ignore the negative ones. Okay. So this helps us to not have to constantly add positive divisors in front of everything. So when I talk about the set of divisors of some number, I don't include the minus divisors. This is particularly nice when later I'm going to talk about common divisors and greatest common divisors. I don't want to have to say greatest positive common divisors and stuff like that. So I'm just going to completely ignore those for the most part, and it's not a bad thing to ignore them. Again, we're not really missing out on any info there. We're just not slapping a minus sign in front of those things. Okay, so basic things, and again, you've actually probably proven these at some point in the past already, but helps to see some of these arguments again. So next is a proposition. Okay, so assume that you've got three integers, a, b, and c. So a, b, and c are integers. If a divides b and b divides c, then a divides c. So what is this saying? It's saying that this division symbol satisfies this transitive property, right? A divides b and b divides c, then a divides c. So quick proof of this is just by definition, right? What does a divides b mean? So a divides b implies that there exists some integer k, right? So there exists an integer k such that b is equal to ka, right? But b divides c implies that there exists some integer, say m, right, such that, I should have put a such that here, such that c is equal to m times b. Okay. Restating this, what do I have here? So c is equal to m times b, which is equal to, since b is equal to ka, this is equal to m times ka. Of course, multiplication of integers is associative, so this is mk times a. And this mk is an integer because multiplying two integers is also an integer. So that's an integer. So I have a times an integer is equal to c, and that is the very definition of a dividing c. All right, that's it. Now you might ask yourself, like, how much of this would I have to say if I was proving this? We're at the point in this course where you don't have to go through the hassle of writing out in words, okay, the integers are closed under multiplication, m times k is an integer, or you don't have to write out in words, that there's associativity, I can move these parentheses. You don't have to worry about writing that out. Just the simple thing like this, right? Written out in exactly this way with no additional words is perfectly fine. Okay. So, questions about that? All right. So, to keep going, here's another useful fact. So, assume that I have five integers, a, b, d, x, and y are all integers. So I have 5 integers there. Then if d divides a and d divides b, then d divides ax plus by. Okay. So, before I even start the proof, what is this saying? So I've got 5 integers, a, b, d, x, y. So everything in there is an integer. I'm saying if d divides a and d divides b, then d divides this expression involving a and b, ax plus by. You might recognize this is a linear combination of a and b, right? So another way of stating this is that every divisor of both a and b divides any linear combination of a and b. Right? So this is called a linear combination of a and b. So ax plus by is a linear combination of a and b. Okay. So quick proof here of this fact. So we'll say a be m times d. Right, so d divides a means I can let a be m times d. Let b be n times d. Okay, that's what I get from d dividing b. All right, then I just write out this linear combination, ax plus by. This is equal to mdx plus n dy, right? Which is d times mx plus ny. Well, this is a linear combination of integers. It doesn't matter whether you call it a linear combination of x and y or m and n. Any linear combination of integers is also an integer. So this is integer times d is ax plus by. So by definition, d divides ax plus by, and that's it. Okay, so these facts are pretty trivial, but it's important to at least see this stuff written out like this. Quick corollary of this is the following. So again, assume a, b, and d are integers. Then if d divides a and d divides b, then d divides the sum a plus b, and d divides the difference a minus b. Okay, I'm not even going to write out the proof, because the proof, this is a corollary of this proposition, because you can just set x equal to, so for the first one, you can set x and y both equal to 1. For the second one, you set x equal to 1, y equals minus 1, right? That does it. So, this is a neat fact. If you know that you have a divisor of, a common divisor, we'll call d. So a divisor that divides two different numbers would be called a common divisor of a and b. So d is a common divisor of a and b. I'll take that here. I'll say this means that d is a common divisor of a and b. we'll get into that later. But what I want you to note right now is that note that for any two integers a and b, I can always talk about the set of common divisors. And when I talk about the set of common divisors, I'm always assured that that set is non-empty. And the reason why I know that that set is non-empty is that, well, any two numbers have at least one common divisor, and that's 1, right? Okay. So 1 is a common divisor of any two numbers you want to pick, any two integers. When I say a number, typically I mean a positive integer. Sometimes I'll just mean an integer. Hopefully there's not too many instances of confusion resulting from that. Okay, so here's some very, very basics that we're working through. Okay, some quick definitions that everyone already knows. So, definition of prime and composite. Okay, so a prime number is an integer p greater than or equal to 2 whose only divisors are 1 and p. So a prime number is an integer that only has two divisors, 1 and itself. Okay. So I'm going to write out what a composite number is. So a composite number is an integer n greater than or equal to 2 that is not prime. Okay. Okay, so a couple of things I want to mention first. So one, it's clear that you pick any integer you want to, so long as that integer is not 1, the least amount of divisors it can have is 2, right? So another way of phrasing this statement of prime number is a prime number is an integer greater than or equal to 2 that has the least number of divisors, right? It has the minimum number of divisors, which is 2. Now you might say, okay, what's wrong with 1 being prime? So 1 is an integer, and its only divisors are 1 and 1, so 1 and itself. So what's wrong with 1 being a prime number? There would be nothing wrong with 1 being a prime number. We could include 1 as a prime number. In fact, some writers in the past actually did include 1 as a prime number. But there's several reasons why it's a good reason not to include it. So the main thing is purely so that we get a much nicer statement here in a little bit. So where we are headed is like our first kind of big named theorem is the fundamental theorem of arithmetic, which definitely has a very important sounding name, and it is a very important theorem. It's expressing something you actually already know, and it's that every integer can be expressed as uniquely, right? There's a unique factorization of that integer as a product of primes, okay, possibly with repetition. Okay, so essentially what this says is that you can take any integer you want to, you can factor it into a list of prime numbers, right, raised to some powers. And the way that you do that is unique. So there's only one way to do it. So, apart from rewriting 2 times 3 as 3 times 2, right, apart from reordering stuff, doing stupid stuff like that, it is a completely unique representation. If 1 were allowed to be prime, you wouldn't be able to say that. So if 1 was allowed to be prime, then you could tack on as many 1s as you wanted to. right? So pick any factorization of an integer you like. You can say, okay, here's a new one. It's that factorization times 1, or that factorization times 1 times 1 times 1, right? And technically, if 1 is being included as a prime, those would be 3 different factorizations you came up with for the same number. And the uniqueness of the factorization is a really, really nice thing that helps us. So that's the main reason why 1 is not included as a prime. Okay, and I think that's a good enough reason to not include it. Okay, so anyway, so prime number is an integer, has only divisors 1 in itself. Composite number is just not prime, right? So you all already know that. So here's a quick fact, which again you've probably seen before in some form. So I'm going to do 2 facts. The second of which you will have definitely seen previously, and it has a really nice, slick, famous proof. But the first thing is a lemma that we're going to use in the next fact. So one, every integer greater than 1 is either prime or is divisible by a prime. Now, the thing to note about this is you might say, wait, I already know more than this. I already know what you said. I already know that actually any integer can be written uniquely as a product of primes. So, I already know something better than this. That's true, but we haven't proven that yet. So we're not going to do that until I think chapter 4 is fundamental theorem of arithmetic. So we're not quite there yet, so we've got to start somewhere. Here's the first preliminary result. Of course, this follows immediately from the fundamental theorem of arithmetic, but we can do it without that. How do I do this? How do I prove this? Well, if I fix an integer n and it's prime, then I'm done. So I don't want to be done immediately, so I should assume I fixed some integer in and it's not prime. If, like I said, if it were prime, I'd be done. So let's say that it is not prime, and then we have to show that it's divisible by a prime. So if an integer n is not prime, then, well, if it's not prime, it's composite. And what does this mean? So a prime number is a number is only divised by 1 in p. If an integer is not prime, then it's divisible by some integer, right? It is divisible by some integer. Call it a sub 1, with a sub 1 being strictly between 1 and p. So you might have been wondering, how is I going to use the fact that this is not prime? If I didn't know that this was not prime, I wouldn't be able to say that I could find an integer strictly between those, right? If my integer n were prime, then maybe this wouldn't be a strict inequality, right? If it was prime, then actually it would have to be either one or the other. This couldn't be satisfied. So if it's not prime, it's divisible by some integer strictly between 1 and p. Sorry, not 1 and p, 1 and n. There we go. Okay. Right. Okay. Now, if a sub 1 is prime, I'm done. Why? Well, I'm trying to show that every integer greater than 1 is either prime or is divisible by prime. So I started out with the assumption that I'm dealing with an integer that's not prime. I want to show that it's divisible by a prime to be done, right? So it's divisible by some integer, strictly between 1 and n. But if that integer is prime, then I've shown that n is divisible by prime, so I'm done. All right, so I must assume that this is not prime, right? So suppose a sub 1 is not prime. All right. Then it must be divisible by some integer a sub 2 such that a sub 2 is strictly between 1 and a sub 1. Okay. Now, if a sub 2 is prime, I'm done. We have to think a little bit harder about this one, why I'm finished in this case. So, if a sub 1 is not prime, for the same reason as the above, it must be divisible by some a sub 2 that's strictly between 1 and a sub 1. But if a sub 2 is prime, the reason I'm done is because I have an a sub 2 that divides a sub 1, and a sub 1 divides n, so a sub 2 must divide n, right? Maybe I can write that in parentheses. So a sub 2 divides a sub 1, and a sub 1 divides n, implies, by that first proposition that we proved earlier, that a sub 2 divides n. And so if a sub 2 is prime, I have found a prime divisor of n, and I'm done. Okay, that's what I was looking for in order to be done. So in order to not immediately be done, right, if a sub 3, or sorry, if a sub 2, I'm getting ahead of myself, if a sub 2 is not prime, then it is divisible by a sub 3. I'm not even going to finish that thought. I'm just going to write dot, dot, dot. What does this mean? If I continue this process out, if I keep doing this, what am I getting? I have a sub 1, which is greater than a sub 2, which is greater than a sub 3, which is greater than a sub 4, and this just keeps going, right? And all of these, using this fact repeatedly, all of these are divisors of n, right? All are divisors of n. Okay. So I have a list of decreasing divisors of n. These are all strict inequalities. Well, what's the problem with this? The problem with this is, by my setup, every single one of these has to be positive. So I have a positive sequence of divisors, right? I have a positive list I should say I have a list of positive integers, each of which is a divisor of n. They can't continue on like this indefinitely, right? The only way that this could continue is if my integers were allowed to be negative, right? Then they could keep decreasing forever. So this can't go on forever. So this has to stop at some point. Okay, so this must terminate. This must stop. This must stop at some a sub m. Now, this is technically an application of the well ordering principle, so if you don't remember that from your 310 class or wherever you first heard about well ordering principle and the things that it's equivalent to, you can have a look at that. I think it's included in the appendix in this book, but it shouldn't be that hard to intuitively see. This has got to stop eventually. It stops at some a sub m, but then this must be prime. And since I can just crank back up and say that a sub m must divide a sub m minus 1, must divide a sub m minus 2, and all these, since I have this fact, right, all the way up to n, I know that this thing actually must divide n, right? So I have found a prime divisor of n, and so I'm done. Okay. So it's a pretty intuitive lemma, of course, and like I said, we're going to get to things that are technically stronger than this, but the main use of this is in the following fact, which, as I've said, you have seen before in some fashion. So theorem, the textbook calls it Euclid's theorem. I'm just going to write it as a single statement. There are infinitely many primes. Okay. Oh, I'm writing off the camera. Okay. So what's the proof that there's infinitely many primes? So maybe some of you know this by heart here, because this is a pretty neat trick. It's not exactly the proof that Euclid used originally, but it's pretty close to the proof that he used. In fact, this textbook's kind of neat. It includes Euclid's original proof in the next chapter. I'm not going to go over it, but you can read 2.3 if you like, because it's pretty fun. Anyway, okay, so there's infinitely many primes. So how do I prove this? Well, there's idea. Suppose not, right? This is, of course, used early on in a lot of proofs courses to show the power of a proof by contradiction, because this is kind of one of the best ways of showing the power of contradiction, because you think about what you would actually do if you didn't have proof by contradiction at your disposal here. Showing that there's infinitely many of something, it's kind of hard to get your hand on that, at least in this way, since you don't have like a function you could plug infinite values into that generates all the primes. You don't have anything like that at your disposal. So without something like that, where you could make an argument like, oh yeah, there's this generates all the primes, there's definitely many things I can plug in, it's always a prime. That's without something like that, right? It's kind of hard to get your hands on something. So contradiction is obviously a natural thing here. So suppose not, i.e. suppose that p sub 1, p sub 2, all the way to p sub n are all the primes. So there, suppose not. If there's not infinitely many primes, then I can just list them all out, and I'm going to do myself a favor here and list them all out in order, right? So p sub 1 is 2, p sub 2 is 3, and p sub 3 is 5, and so on, right? I'm just going to list them all out in that order, okay? All the way up to the largest prime, p sub n. Okay, so idea. Form the number n defined to be the product of all of those primes plus 1. And you know exactly where this is heading. So claim n is prime. And that will do it, right? If I can prove this claim, then I'm done, because I've arrived at a contradiction. The reason it's a contradiction is I said immediately that I listed all the primes. The idea is that I define a number that's the product of all those primes plus 1. And if this is prime, well, this is a prime number that is not in that list that is supposed to be a completely exhaustive list of all the primes. So clearly a contradiction, because this number is not in the list. Okay, so how do I prove that this is prime? Okay. Well, if it's not, then what can I say? By this previous lemma that I proved, every integer greater than 1 is either a prime or is divisible by a prime, right? So if n is prime, my proof is complete. It's kind of a weird format I've taken here because I'm claiming that n is prime. I'm really this sentence here kind of belongs outside of this what I've written here, but that's fine. So my proof's complete by contradiction because I said that I listed all the primes, but here's n that's clearly not on that list that is also prime. So if n is not prime, well, if n is not prime, then it is divisible by some prime by the previous lemma. Okay, because previous lemma said it's either prime or divisible by some prime. Okay. Well, that's a little weird because now I'm going to call my some prime p, right? So my some prime I will call p. So I have p divides n, but also p divides the product of all those primes. Why? Well, because it's one of them, right? P is one of these primes. Okay, so because I said that this is my total list of primes, some prime P has to be a divisor of n. Well, the only thing that it could be is one in that list, so it definitely divides this product of all these primes because it's one of them, right? It's some P sub j. All right. But the product of all the primes, that is actually what in terms of n? It's n minus 1. So P divides n, but also P divides n minus 1. Thus, P divides n minus n minus 1. Why can I say that? Because any common divisor of a and b also divides the difference a minus b. So if p divides n and p divides n minus 1, then it has to divide n minus 1. But what is n minus 1? It's 1. That's a contradiction. I can't have p a prime dividing 1. Okay, that can't happen. So then where is my issue here? My issue here was I assumed that n was not prime. So then n has to be prime. But if n is prime, I have constructed a number that is larger than all of these primes, so it can't be on this list, that is prime, and it's not on the list of all primes, so n is prime. So this implies n is prime, but n is not on my list of all primes, which is another contradiction, which I'll denote by these two implication arrows facing each other. All right, and that's it. Okay, so that's the proof. There's another proof listed in the same section that is very, very similar, uses factorial. It's very, very similar in structure. And another proof, you can read 2.3 for Euclid's original proof. Okay. All right. So that's that. Now it's 12:19. I only have like a minute. This won't take me longer than a couple of minutes here. One more thing I wanted to say before I get into the division algorithm tomorrow, which is this sieve of Eratosthenes. So it's really quick. Nothing too too fancy here. In fact, oh, there we go. In fact, this is kind of like one of the most crude tools for analyzing primes, but it is kind of neat. Oh, I should say, yeah. So a good question here that's brought up: is it possible that n is composite but it's divisible by primes not on the list? Yeah, yeah. So actually, I'm not going to go over this. I'll spend the last minute talking about this fact. So going back to this proof, there is a very, very common misinterpretation of this proof that is really, really common. In fact, I think maybe even the first time I saw this, I also thought the same. I made the same error, and it wasn't until a little bit later that I realized that it was wrong. So the idea to form this might lead you to think that if you take the first, say, 10 primes, right, or the first however many consecutive primes you feel like, and you multiply them all together and add 1, that the thing you get is necessarily prime because it worked here. As someone is pointing out here, yeah, exactly. It first happens if you do the product of all the primes up to 13 plus 1, that is composite. It's 59 times 501. Yeah, so the thing is that what makes the proof work here is the fact that there's a very key part of this expression here, that you're saying that these are all the primes. Okay, that's why it works. So the reason why this is in general not prime, when you try to do this for some number of primes, is that it's that this is not prime because the contradiction comes from the fact that you've constructed it using a list of what you claimed are all the primes. Okay, so the reason that it fails is exactly, if you notice in this example that was given, there is a prime that is a divisor of that constructed n, that is 59 here, is a prime that is not on that list, right? So that's why the proof still works, because nothing has failed in that case. Yeah. So that is a common misconception that some people get out of the when you do this construction. Yeah, this is not in general prime if you just go up to some. So it's very important that you have the assumption that these are all the primes. That's what gets you across the finish line. So anyway. So tomorrow I will start with the division algorithm, and I'll slightly modify our schedule by shifting some stuff around. That's why I only list up to a week. That way, we never get out of sync with anything. So anyway, yeah, and hopefully I won't have technical issues at the very beginning, so that it's not totally weird and I can actually see the YouTube playback. But anyway, so. I think that's all I was gonna say for today. So like I said, tomorrow we'll finish the rest of chapter 2 and start on chapter 3. I think I should be able to finish that tomorrow. But anyway, so I'll hang around for another couple minutes if you all have questions. But other than that, I will see you all tomorrow. So no homework will be assigned until maybe after tomorrow's lecture. Either tomorrow or Wednesday is when there will be homework. So tomorrow's lecture is still going to be synchronous. Wednesday's lecture, I'm just going to record it and upload it sometime, either Tuesday evening or Wednesday morning. But anyway, that's the plan. So I will see you all tomorrow.